So, during this session I will be taking up some more numerical problems on quality and reliability. Just to remember one particular aspect, that is the kinds of problems we are dealing with. These are typical related to quality and reliability. Obviously, we have covered a large number of topics till date, and given a particular problem, you must understand that which aspects of quality or reliability or quality and reliability this problem refers to. And while you solve a particular numerical problems, so you follow a systematic approach, and sometimes just referring to one particular numerical problems may not be enough in understanding the concepts. So it is supplemented with many case studies. So during assignments of your while we provide the assignments to you, now sometimes in the short cases also we may include, and obviously this understanding of these numerical problems will help you in addressing those case studies. Okay, now let us talk about the next examples or next numerical problem. Like here what you find, there is a system structure given, right? So these are this is the system structure. You have one parallel configuration. Now this parallel configuration is linked with the two other components. This is in series, and similarly all these four components, they are also in series, and this is one subsystem, this is one subsystems, and these two subsystems are in parallel, and then this parallel subsystems is linked with one particular component over here and another component over here in series. So, okay, so it's a typical example of a network indicating a combination of series and parallel structures. So determine the system's reliability for the network shown in figure. Find the system's reliability if R equals to 0.98. That means what we have ensured that all the individual components, they are having the same reliability. Is it okay? And the components may be different. Obviously it will be different, and in any system, but how do you ensure that whatever may be the design of a particular component, make sure that the reliability is very high and they are almost same for the reliability value is same for all the components. So that is a very the challenging assignment for any designer. So how do you get the solutions? That means R top. That means you look at there is a two structures. You have the top one, you have the bottom one. Is it okay? So this is the reliability of the systems on the top. That is R into this one. That means 1 upon 1 minus R to the power 3. That means the three components are in parallel. So you have the parallel systems reliability, and it is linked with two other components in series. The first one, then you have the middle one, that is parallel systems, and it is the third one. So this is the middle one's reliability, this is the first one's reliability, this is the third one reliability, and they are in series. So that's why it is like this one. And what about the bottom one? Bottom one means there are four components, they are in series, that's why it is R to the power 4. And what is the systems? Systems is, we will have this one and this and this is the outer one, the systems. There is the component R1, this one. This is the middle one. Is it okay? So ultimately, you have this expression, the simplified expressions. You have the reliability for the top portion or the top systems. This is the reliability for the bottom systems. So ultimately, when you assume that R, the value of R or the value of reliability is same for all the components, and this value is assumed to be 0.98, considered to be very high, then you can compute the reliability for the top systems and reliability for the bottom system. So it is 0.9604 and this is 9224. Obviously, what could be the possible reasons that the bottom system has got lesser reliability? Why? Because it is, you can explain like always, if the system is in series, so series configuration, the system's reliability is expected to be lower. And then the overall system's reliability, you have these expressions over here. So you just you take the value of R as 0.98 and you compute this one. This is known, this is also known, and ultimately overall system's reliability is found as 0.9574. Okay. Now let us talk about the next example. Determine the reliability of the standby system shown in figure. Is it okay? Now the standby systems we have already explained, and if you recollect, we say that there are several ways you can improve the reliability of a system. So one approach or one way to improve the reliability of the system is creating a system with standby. That means if the main system fails, obviously the standby system will start working automatically. So that is the basic the logic, that is the basic rule. So the reliability of the standby system you have to determine. Each component has an exponential time to failure distribution. That means we are saying that these components are not in the burn-in phase, but they are in the useful life phase. Okay, you refer to the life cycle curve. The failure rate of each component is 0.003 per hour, and the period of operation is 400 hours. That means you need to check that whether the system will run for 400 hours or not. Is it okay? And when it runs, whether you are getting the intended function or the operation from the systems or not. So that is your main concern. Find the mean time to failure. Okay, so you have to apply a formula, and then you have to compute this value. If the three components are arranged in parallel, find the reliability of the systems. Is it okay? And the last one is find the mean time to failure for the parallel systems in part C. Now here one point I like to highlight, like say most of the time we are computing the value of say the mean time to failure. Is it okay? The system wise, component wise, we are calculating this one. Now another term we have used, that is the MTBF, that means mean time between failures. And there is a difference between so the mean time to failure and mean time between failures. Now supposing you are asked to compute the value of mean time between failures. Now what are the the additional data you must call for so that the MTBF you can calculate. Is it okay? So I think my question is clear. That means you need to collect data, okay, some additional data, so that you are in a position to calculate the mean time between failure. And then if you find that there is a significant difference between these two, that means between MTTF and MTBF, what does it mean? That means related to the system's operations or related to the condition or related to the state of the system. Is it okay? So you know why there is a difference between mean time to failure and mean time to failure and mean time between failure. Is it okay? So obviously there could be several examples on this. Now let us talk about these examples. So the failure rate lambda for each component is this 0.033 hours. For 400 hours of operation, the system reliability is this one. That means RS is e to the power minus lambda t into this. Is it okay? We have already computed. That means what we have assumed. How do you get this expression? That means we are assuming that if the time to failure is exponential with the corresponding parameter value, that is lambda, that means the number of failures will be Poisson distributed with the corresponding parameter value lambda t. That means number of failures within a time period of t. Is it okay? T may be 1 hour, T may be 300 hours, whatever the number of failures. So you can prove it that it is Poisson distributed with the parameter lambda into t. So that's why it is e to the power minus lambda t into 1 plus lambda t square divided by factorial 2. You just refer to our original expression for the systems with standby components. So there is a general expression, that means if you have a basic component with n number of, say, the standby components, and how this the standby systems is working. That means at any point in time, make sure that at least one component must run, and so that the system runs. That means system design is such that it depends on ultimately the operation of one component among n plus 1 components. Is it okay? So this extra the components you have added, that is n number of components, in order to improve the reliability. Many a time it reflects the level of redundancy in the system. So now you have all this data, lambda value is known, t is given as 400 hours. So ultimately you get a value of 0.879. Now what is the mean time to failure? That is, we have already have this expression, that is n plus 1 by lambda. Now how do you get this expression? So this is another problem I set. So why don't you as a learner, as a student, you derive these expressions, that is MTTF is equals to n plus 1 by lambda when you deal with systems with standby. And how many standby components you have? N number of standbys. So you need to derive this expression. So here n is 2, okay, and so n is 2, that's why it is 3, and lambda remains same. So lambda is 0.003, that is MTTF is simply 1000 hours. If the system has all three components in parallel, that means many a time you are in a fix. Why do you means whether I will opt for a systems with standby, or but I will say that let the system remain in parallel structure. So in most of majority of such cases, you need to compare the standby systems with the parallel system. So if the system has all three components in parallel, the probability of failure of each component is obviously, that is F for the first failure probability. For the first one, that is 1 minus e to the power minus lambda t. So this expression also we have derived, you refer to this expression. So this is, that means lambda is 0.003, 400 hours, that is the value of t. So you get 0.6988, that is the failure probability. So obviously if you have three components, so 1 minus 0.69883, and what we are assuming that all these three components, they are not only similar, they are also identical. How do you define identical? with respect to their the time to failure distribution as well as the failure rate. Is it okay? So, so what is the system's reliability? System's reliability is just 0.659. So, the mean time to, you can compare this value with the reliability of the systems with the standby. Is it okay? So, the mean time to failure for this parallel system is given by MTTF 1 upon lambda 1 plus 1 upon 2 plus 1 upon 3, and then you get a value of 611.1107 hours. We observe that the system reliability and the MTTF of the standby process differ significantly. Now, MTTF for the standby system, it was 1000 hours. If you opt for a parallel system, it has come down to 611 hours. Is it okay? So, from this perspective, that means from the in respect of MTTF, obviously the standby system is better, and similarly in respect of the system's reliability, the standby system is better. Now, the next example, that is example 8. What what we have assumed that if you remember that exponential time to failure distribution is a special case of say Weibull time to failure distribution, right? And when you refer to Weibull distribution in Weibull distribution is having 3 parameters. So, the gamma, that is the first parameter, this is referred to as the location parameter. The value of gamma may lie between minus infinity to plus infinity. And then you have the shape parameter. The shape parameters, the notation is beta. So it is greater than 0, and that means it's a non-negative or the positive. And then alpha is basically the scale parameters. So when you assume that the distribution is Weibull, then when you refer to the reliability modeling or reliability analysis, there is a reason that we assume that the value of gamma is assumed to be 0. That means the location parameter doesn't have any influence on this. Is it okay? But you can select the possible values of the other 2 parameters like say beta and alpha. Now, in this example, what we are referring to? We are referring to the design of an electromechanical systems. There are many such systems, surrounding you. So, in the design of an electromechanical system, 4 major subsystems have been identified. So, what are those major subsystems? 1, 2, 3, 4. Each having a Weibull failure distribution. Actually, it is Weibull. Whenever you say failure distribution, it means time to failure distribution with the parameter values as follows. So, what are those parameters values? The scale parameters theta or alpha, whatever it is, and the shape parameter beta I have already mentioned. Is it okay? Now, these are the values you have obtained. That means this is a subsystems. Now, this is 6.3, this is 0.89, this is 7.7, this is 0.79, all are greater than 0. For the third subsystem, it is 10.7, it is 1.79, and for the fourth subsystems, it is 12.3, and the value of beta is 0.89. Now, my question is, how do you get these values, 6.3 or 0.89? So, just think about it. Is it okay? Means if you are asked to get these values, so which procedure you follow, which technique you apply? Getting my point? So later on we may take out these issues, that how do you get these values of say scale parameter and the shape parameters. Is it okay? So keeping aside for the time being these questions, now let us talk about this problem. So, if the desired reliability of the system is 0.987, consisting of all these 4 subsystems, at the end of the first 2 years, it's clear. Find the percentage increase in reliability for each of the major subsystems needed in order to reach the system's goal, assuming all the subsystems have equal reliability goals. Is it clear? So, I repeat, if the desired reliability of the system is 0.987, okay, the question is raised. Why do you specify 0.987? What is the basis? Is it okay? As I have already told you, that whenever we deal with the reliability issues for a particular product, many a time we assume that the product is at the prototyping stage. Is it okay? So, during the prototyping stage, you carry out a lot of experimentations, so that ultimately when you analyze the results for different design alternatives and for different structure, for different system structure, you say I have got several alternatives, and the expected value of reliability for an alternative is this one. Okay, so you do experiments. So, supposing during experimentations you find that this is a value 0.987. You have already you say that this is an acceptable value 0.987. It could be 0.98 or 0.99 or say simply 0.97. So, some value you must specify, okay, so that your recommendations are very specific. So, that is the basic purpose of assuming such a value. Find the percentage increase in reliability for each of the major subsystems. So, these are the major subsystems. So, how do you proceed? Solution is, this is for a given systems, e to the power minus t by theta into beta. That means for a single component, assuming that the time to failure is Weibull. So, this is basically your expressions for the reliability for the time period t for a component. So, theta is basically the scale parameters and beta is the shape parameters. Okay. So, we have already referred to the Weibull the density function and the reliability modeling we have done. So, please refer to those expressions. Now, this is the first subsystems. Is it okay? So, the first subsystem, these two values are given. For the first subsystems, the value of theta, that is the scale parameter, that is 6.3 and beta is 0.89. So, you are applying this formula to get the reliability for say for the first subsystems, that is 0.6976. Similarly, for all other subsystems, major subsystems. So, major subsystems 2, that is the value of theta is 7.7 and 0.79 is the value of beta. So, you get a value of 0.7084 as its reliabilities, and similarly for the third subsystems the value is 0.9515 when beta value is 1.79 greater than 0 and the theta or alpha is 10.7, the scale parameter, and similarly you compute the fourth subsystem's reliability with the values of beta 0.89 and alpha or theta 12.3, that is 0.8199. Now, if the system is in series, so you just multiply all these values, is it okay? It's a product term, and you get a system's reliability as 0.3858. So, what is the reliability goal? The reliability goal is, if you have 0.987, is it okay, in series. So, the individual component reliability should be this one. Is it clear? Because the system's reliability is this must be reliability goal. That means the system's reliability is 0.87, that is r to the power 4. Is it okay? So, obviously, this will be the expressions for the individual component reliability. Is it okay? So that the system reliability becomes 0.987. So this is individual component reliability is as high as 0.996734. Okay. So what is the percentage increase in the subsystems 1? So simply you calculate, that means here it is 0.6976, right, and what the increment you require, you must have this value 0.996734. So what is the percentage increase? That means the desired value minus the actual value divided by the actual value into 100. So percentage increase in the reliability of the first subsystem, that is 42.88. And the same way you calculate for the subsystems 2, subsystems 3 and subsystems 4. So it was 0.7084, now it is to be made 0.996734. So what is the percent increase? Same formula you use, that is 40.82% increase is required. Similarly for subsystems 3, you need to improve 0.48, only just 4.84%. That means subsystems 3 is as far as reliability is concerned, it is a very improved systems, and its quality must be very high. Is it okay? So whenever you say that the reliability is very high, immediately you assume that the quality also must be very high, quality of the systems or the quality of the component. So it is 0.9515. So obviously just 4.84% increment is required, whereas the fourth subsystems you need an increment of say 21.67%. Now the next examples I will go through quickly. Assuming the redundancy is the only way of achieving further reliability growth for each of the subsystems in example 8, that means you refer to the previous examples. Find the minimum number of redundant units of each necessary in order to achieve the component reliability goals. Is it okay? You have set the target, right, and you know what is the current value of reliability. So the major subsystems is this. Again I am telling you that what are the the scale parameters. This is very important, and similarly the same parameters. So these values remain same. So what is the solution? Solution is this, right. So this is a parallel systems, n components in parallel, and so the value of n will be this one, right. So therefore n1 is, you calculate n1, that means this is the your desired value, this is the actual value. Is it okay? You are here, you want to reach here. Okay, so what will be the corresponding value of n1? That means the 6 units is actually it is 5.1126. So the number cannot be a fraction. So it is made, you round it off, so it becomes 6. Similarly for the next subsystems, so this is your desired value. Is it okay? And this is your actual value as of now. So what is the corresponding value of n2? I have already given the expressions for r. So here unknown is small n. So how many components you require? That means you require 4.6449, and that means it is a 5 units. And similarly for the subsystems 3, you need 2 more units to be added, and as you know, as a redundant one, that means it is essentially the systems with standby. Is it okay? The more standbys you add, that means the more the redundancy you add to the system, and this is one way you can improve the reliability of the systems. And similarly the fourth subsystems, you need to consider 4 units. Is it okay? So that you can achieve this target value of reliability from the existing 0.8199. Is it okay? Okay, so we have covered a number of we discussed a number of numerical problems related to quality and reliability. So I advise that you go through all these problems, and later on many such so the numerical problems and will be given to you as an assignment. Okay.